Assalamualaikum and hi students. This is a lecture video for BMCG 1013 Differential Equations. The last topic for this subject is Partial Differential Equation Chapter 5. So the learning outcomes that will be covered in this lecture video are to identify the order, linearity, homogeneity and classification of the partial differential equations PDE. And then to understand the method of separation of variables, and the last one is to solve the initial boundary problem of PDE using separation of variable methods. 5.1 Introduction to PDE, partial differential equations. So PDE is a differential equation which contains partial derivative with respect to two or more independent variables. Okay, so we just recap what we learned in chapter 1. So basically PDE used to formulate and solve problem involving functions of several variables such as the propagation of sound or heat, electrostatics, electrodynamics, fluid flow and elasticity. The three special cases of PDE, we have the first one, Laplace equation, del square u over del x square plus del square u over del y square equal to 0. The second one, we have heat equation, k del square u over del x square equal to del u over dt with k a constant. And the last one, we have wave equation, alpha square del square u over del x square equal to del square u over del t square. And also alpha is a constant. For the order, linearity and homogeneity of PDE, you know that the order of PDE is the highest order partial derivative involved in the equation. Example 5.1, state the order of the following PDE. Okay, we have that for A, we have del u over del z plus 2 del u over del y minus 3 del u over del x equal to 3x minus 2y minus z. So the highest order is order 1. So for this one, this is order 1. Okay, the second example, B, you have del square u over del y del x plus del u del x to the power of 3 equal to 0. So now the order is 2. Because the highest order for this PDE is 2. This is del u del x, the first order. Okay. And then the last one, C, del cube u over del z del y del x minus del u over del x plus u to the power of 4 equal to del u over del y. This is the first order, and this one is the third order. So the highest order here is order 3. And then the PDE is said to be linear if all the partial derivatives are of the first degree and no products of dependent variables and derivative occur. So a linear second order PDE can be written in the form of A del square u over del x square plus B del square u over del x del y plus C del square u over del y square plus D del u over del x plus E del u over del y plus F u equal to G. Okay, so A, B, C, D, E, F and G are the functions of x and y, and it can be constant as well. Okay, it can be 0. I mean, you can have A del square u over del x square with B 0. So you don't have this term. Okay, so for example 5.2, state whether the following PDE are linear or not. Okay, so for the first one, you have C del square u over del x square equal to del u over del t. So basically this is equal to C del square u over del x square minus del u over del t equal to 0. So the G is equal to 0. So it is linear. Okay. And then for B, del square u over del y square plus del u del plus 2u del u over del y equal to 0. So since you have a product of your dependent variable, u is your dependent variable, multiply with the derivative, so this is not linear, non-linear. Okay, the third example, you have del u over del z plus del u over del y to the power of half. We have square root over here, plus 3 del u over del x equal to 0. So because of this, because your derivative are not first degree, is not because your derivative is raised to power, to the power of half, so this is non-linear. Non-linear PDE. Okay, and for the last one, you have del cube u over del y del x square minus del square u over del y square equal to cos y minus cos plus cos y. So this is linear, okay, with your g equal to cos y. Okay, so this is linear PDE. Next, from the triple asterisk. Okay, so from here, from this equation, if gxy is equal to 0, so the PDE is homogeneous. Otherwise, the PDE is called non-homogeneous. If g is not equal to 0, so it is non-homogeneous. Example 5.3. State whether the following PDE are homogeneous or non-homogeneous. So in this case, in this first example, you have your gxy. Gxy is equal to xy. Okay, so since it is not equal to 0, so this is non-homogeneous PDE. Okay, and then second one, you have del u over del z plus del u over del y equal to del u over del x plus 0. Okay, because you don't have g. So this case, gxy is equal to 0. So this is homogeneous PDE. Okay, C, have this with, okay, if you move this negative exponent xy, so it is the g. Gxy is exponent xy. So it is non-homogeneous. Okay, and the last one, it is homogeneous. Your g is equal to 0. So this is homogeneous PDE. And again, for classification of PDE, we refer to the general form of second order. So you know what is the A, B, and C. So from A, B, and C, we can classify the PDE. Okay, whether it is hyperbolic, parabolic, or elliptic. So A, just focus on del square u over del x square. B is for del square u over del x del y. And C for del square u over del y square. Okay, just ignore what is D, E, F, and G. Just focus on these three first term. Okay, for classification. If b square minus 4ac is greater than 0, it is hyperbolic PDE. And if it is equal to 0, it is parabolic. Lastly, if it is less than 0, it is elliptic. Example 5.4. Classify the following PDE. For Laplace equation, we have three special cases. So, first we have Laplace equation, del square u over del x square plus del square u over del y square. So, first list down what is A, B, and C. A, B, and C. So, A is here. We have 1. A del square u over del x square. B is for del square u over del x del y. So, we have no B here. So, 0. And then C, we have C del square u over del y square. So, it is equal to 1. Okay. So, substitute into b square minus 4ac. We have 0 square minus 4 multiplied by 1 multiplied by 1. And we have negative 4, which is less than 0. So for Laplace equation, it is an elliptic equation. Elliptic PDE. Okay. And then for B, heat equation. K del square U over del X square plus, equal to del U over del T. So A is equal to K. B is equal to 0 because we have 0 del square U over del X del Y. And then C is also equal to 0. So this is K del square U over del X square minus del U over del T equal to 0. For del U over del T, this is D. So we don't consider the D. Okay, so we just have to find what is A, B, and C. So B square minus 4AC equal to 0 square minus 4 multiplied by 0. Sorry, K, this is K. A is K. And C is 0. 0 square minus 0 is 0. So we conclude that this heat equation is actually a parabolic PDE. And last but not least, we have wave equation. For wave equation, we have alpha square del square U over del X square minus del square U over del T square. Okay, with alpha is a constant. So A refer to del square U over del X square, it is alpha square. B del square U over del X del T, where it is 0. And C, we have here negative 1. Negative 1 del square U over del T. So C is negative 1. Okay, so B square minus 4AC is equal to 0 square minus 4 multiplied by alpha square multiplied by negative 1. So we have 4 alpha square. Since alpha is a constant, so it is always positive. Okay, so when B square minus 4AC greater than 0, this is hyperbolic.